Okay, there's actually two presentations here on forming. I split it up so they wouldn't be as long, easier to make into little movies. We're going to be talking about forming methods, hot, warm, and cold methods. And this first set of slides is about hot forming. Okay, we're mostly going to be looking at the metal processes, but there are some plastic and even wood forming processes. Um, and the basics of this is that you're taking raw stock from stock sizes and you bend it or you cut it or you somehow shape it. And the difference between the hot, warm, and cold is based on the melting point of the material. Um, if it's hot working, it's typically done at about 60% of the melting point. Um, Now, there's a lot of metalworking that's done at the melt point, like welding, casting, which we'll be talking about in another presentation. But for the most part, there's something that magically happens to metals, particularly steel, when you're hot working it. Warm working is above room temperature, but not to the to that 60% melting point of the material. And cold working is room temperature. I'll, I'll talk about those two in the next presentation. Now this gets to be a little tricky. The melting point approximately of iron is about 2,800 degrees Fahrenheit. Um, and there's a point with iron at about 1375 um, where it's called the Curie point. Above that temperature, the um, iron, the steel, becomes softer and plastic, and you can bend it by hitting it. Um, just as a little review, carbon steel is about 98% iron and a little less than 1% carbon. Um, and there's trace elements of sulfur and phosphorus and manganese, and sometimes you'll add more manganese to make it harder. Um, and steel alloys are going to be mostly 92 to 98% or 92 to 95% iron with other transition metals. Transition metals are those um, elements on the periodic table just right in the dead center. Um, they're not the noble gases, and they're not the first row materials, but it's just those main ones. Getting into something a little bit beyond this course. Now, the same thing can be true of the copper alloys, bronze and brass. Copper seems to have what you might think is a remarkably high melting point, but that's when it's pure. But it's not very useful when it's pure because it's got to be mixed with tin or zinc, and so that brings the effective melting point down a bit. When you look over on the right side and the hammer forging video in the single process collection, you can see this happening in that one because they get the material up to probably 2,000 degrees Fahrenheit, and then start working it. But when it gets down to um, just 1,400 degrees Fahrenheit, um, the material has changed color. It's harder to shape, and they got to put it back in the oven to heat it back up. And those color changes actually happen as you heat up steel, plain carbon steel. Um, it's a very light straw color when you first start heating it up, and then you get into the bright red and the oranges and the bright yellows. Um, A couple other things considering this: aluminum's melting point um, at 1,220 degrees Fahrenheit, which is fairly low, and generally don't hot work aluminum because it is more ductile than steel. It can be cold worked. You mentioned here plastics. Thermoset plastics are not remeltable, so they're going to be just one-shot deal. Um, and the category of plastics that are called thermoplastics are meltable and remeltable, and their melt points are between 200 and 300 degrees Fahrenheit, and each one has a slightly different one. There are processes for hot working that are not molten processes, but we'll talk about that in a minute. And wood can actually bend wood using a steam oven. Be a good senior project to build a steam vessel for bending wood and then bending the wood. Shove wood in, steam it up for a few hours, bend it, and there you go. Now, what happens when steel is heated to past that Curie point? Is that it enters what's called a plastic state, meaning it can be formed. And that's actually where this was known long before artificial plastics came on the scene. And that was one reason that term was chosen for things like polyethylene, because it was easy to deform. Some other things happen in hot working, and steel is basically, if you get down to the microscopic level, it's a lot like a sugar cube, a bunch of little grains stuck together, and then some big carbon atoms jam in there and make it more solid. What happens is that each atom of iron aligns itself in a perfect alignment, making like a long crystal, where the crystals join together into a matrix that is all in one direction, but they break off at a point and get twisted around and lined up differently. If you have small groups of crystals, you get a much denser material, and if they're smaller, they can be aligned. Think of it again as those sugar cubes that have a certain shape. Well, if they're all pointed in the same direction, you have like a big stick of sugar. And when this happens, some of the other mechanical properties can change. One of it is by aligning those grains into the same direction, you can make things like wrenches stronger. You can see this a wrench that says drop forged. That means that it has been drop forged and that the grains in it that you can't really see unless you get a microscope out run in the direction of the handle for that wrench, making it stronger than one that would be just machined. This is where, if we were able to do this with show and tell in class, I could show you some machined wrenches that are pretty cheap and would break. Well, here's an example of some grains. One on the left is cast, it's copper, but iron does the same thing. You can see the grains line up. If it's cast, that means it was poured in hot and then let cool. And when that happens, the grains align themselves like icicles towards the center. The center is the last part to harden, and they come in from the outside and start going in. Think of it as freezing an ice cube. If you've ever used ice cube trays and you got a party coming up, you want to see if the ice is ready to crack out, and you stick your finger in there and you break through the top, you notice that the top freezes before the middle does. Same thing happens with castings. If you look carefully at the gear blank on the right, you can actually see in the cutaway what the grain structure looks like after this has been forged into that shape. You can see the straight lines in the thin part of the gear and thick on the outside where the gear cogs will be, and they loop around, increasing the strength of this. Think of that as just additional strength to that piece of steel. And so it's with hot working, like forging, or that you can actually manipulate these grains. The other thing that you can do is that if there are any gaps, holes, porosity, steel surprisingly is porous, fresh out of the mill, and if you pound it out, it will. That porosity is eliminated, and some impurities can be broken up and distributed. If there's some chunk of something in there, it can be better off. As I said, the grains get refined from hot working, and the a whole bunch of things: ductility, impact resistance, hardness, strength along the grains increased. So it has advantages in the parts, and if you were comparing a particular material, say half-inch piece of steel that you wanted to bend, you could bend that with cold working, just like Superman bending it. But it would take a lot more expensive equipment because it requires a lot more power to do that. But if you get it hot, then it doesn't take as much force, and you can bend it with just a hammer and an anvil. So it really has some cost advantages. The disadvantages of hot working are that you're dealing with hot stuff, so it's more dangerous. And because it's hot, your equipment's got to be specialized, and the tool maintenance is more difficult because you're taking hot metal and putting it on an anvil and hitting it with a hammer. You're going to slowly heat up the anvil, and you're slowly going to heat up the hammer, and it becomes a bigger problem in rolling. Now, one of the biggest disadvantages is that a scaling happens on the surface. When you get it up to that point, past the Curie point, and then bring it out into the atmosphere, bring it out of the oven, immediately the outside layer of atoms starts cooling off and scales over. And if you look in these videos, you'll see the people pulling stuff out of the oven and either knocking it on a table. What they're doing is trying to knock off that scale before they start working it, or they'll take a brush and brush it before they do that. It's particularly noticeable on the upset forging video. So the scale is a problem. You actually end up reducing the diameter, if you will, of whatever it is you're starting to work with. You can't hold particularly tight tolerances. That wrench from a few slides earlier, the part for the where would go around the bolt would have to be machined to be exactly the right size. You can't get that exact size from forging. So it requires a secondary operation. Okay, we're not talking about welding or casting, but there's some hot forming processes. Forging is one, but there's also rolling, extrusion, and pipe and tube manufacture. There is a hot drawing process, but drawing is really a cold process. We'll discuss that in the cold presentation. rolling, you got a big piece of metal, you got to roll it down to the right thickness you want. And it's usually the first operation for when the metal's going to be um, coming out of the um, metal mill. Over on the right is a diagram that shows what are today called mini mills. Um, they're not the big blast furnace systems, but this is what most steel is made out of. Um, Generally, a lot of scrap. That scrap goes into the electric arc furnace. There's three stages of it shown at the top. And the electric arc furnace is a big crucible with giant graphite electrodes. And those graphite electrodes are electrified, and it's basically a giant welding process. You start heating all this stuff up, and as electrodes lower in and cause the metal to melt from the same process that stick welding does. And they can tip these furnaces, pour out a little bit to test to see what the carbon content is, what the alloys are, and then when it's fully cooked, they'll pour it into a ladle, take that to the casting area, and pour it out. And as it starts to cool off in what's called a trundish, they'll typically have it with have it cool under a inert gas atmosphere so that it won't rust. And then they'll start rolling it. They'll keep rolling it, getting it right, getting it to the right size, chopping it off, and then you have your steel at the end. This is pretty much how a lot of shapes are made. And these are the kind of shapes that would come out of that mill, big slabs or blooms or billets, and they would then be rolled into wire, bars, rails, plates, strips, coils, um, sheets, all kinds of stuff. And you can imagine that you'd have to do the rolling to make that I-beam or those channels, those profiles. Now, the most interesting one is forging. And I've got listed several single process video assignment module videos to watch. There will be questions. And if you've looked at that section, you've seen there's several videos to watch. The classic one is the hammer. That's your classic blacksmith. Heat it up, hit it with a hammer, put it back in the oven, bring it out, heat it with the hammer, put it back in. The anvil is a very interesting device, and it was really very useful when they made custom horseshoes for horses. It's kind of gone away, although there's a little bit of adjustment made, but they basically now have horseshoes like men's shoe sizes or women's shoe sizes, where you just get the right size and hammer it into the foot of the horse. But before they made had customized and established shoe sizes, blacksmiths had to bend those horseshoes one at a time. You also have open die or drop forging, like was made with that wrench. There's a video on that. And these could use what are called auto hammers, as opposed to having a blacksmith actually swing the hammer, but it does effectively the same thing that the blacksmith single hammer would do. There's also some impression forging and press forging. I think there's a video on that. And upset forging that's how you get the head on a nail. The advantages with forging is that it reduces porosity and closes any voids in the metal. If you get it close to the right shape, you don't have to do a lot of machining. It can save some time. And it can improve those properties with improved grain instruction and some heat things that can be done. Disadvantage is you got that scale, so it's got to be cleaned off. And it's a secondary operation. You're going to have to do some machining to it to make it fit, or at least some polishing to get any scale off. And it can be fairly expensive to get all the tooling for mass production right. And there's some custom things, you've probably all watched those videos of the guys forged in steel making swords and the like. There are some short production runs, but you don't spend a lot of money setting up a factory to do short production runs. Or if they are short production runs, they are large pieces, like the axles for railroad cars. Another hot working process is called hot extrusion. It is exactly what it is. The metal is heated super hot and then forced out of a shape, or maybe through a series of dies, till you get the shape you want. It can be done very quickly. This also improves that microstructure, and you can keep some pretty close tolerances. This is how angles and some channels are made, and some other shapes. Particularly handy, and this would be one of the situations where you would have a hot extrusion process with aluminum. Aluminum, you couldn't be able to extrude it melted in a melted form, but you could heat it up enough to extrude the shape of a electronics case, something like that. And here's a diagram of it. The part being extruded is number 4. That's the billet that's going into the dies, number 2 and 3, and the rod that comes out at the end is number 1 over on the left. And you've got a gigantic piston on the back forcing it into the dies. I want to mention here about shaping plastics, and the plastic, some of the plastic processes, the injection molding particularly, but the blow molding, vacuum forming can be start molten. Well, not the vacuum forming. Blow molding can start from a molten process, but it also, the below part of it would be considered just a hot working process, because it's not making you're getting the plastic melted to a point where it can be shaped. And most plastic parts, the most used process for making plastics is called injection molding. And you make a little shape. I may talk more about it with casting, but make a closed die, squirt the plastic in there, open up the die, and there you've got it. Very expensive molds, but you can make a gazillion different parts for that. Blow molding is another way of making bottles, and unfortunately, we were going to be doing some vacuum forming. And vacuum forming is you're forcing the softened plastic around a shape, and then putting a vacuum on it pulls it in tight. There's also extrusion plastic making, and there is a process called plastic welding. It has actually done here. A former student, he earned his way through college doing plastic welding, fixing pallets for one of the citrus vendors that used plastic pallets to move their material around on, and they had to be repaired. They would break, and he had an 8-hour-a-day job welding plastic. And then basically you heat it up with what's kind of like a hair dryer, and then dab in extra plastic like a welding rod, and you build up plastic on it. Okay, the next The companion presentation to this is forming 2, and I'm going to pick up right here where I left off.